Hi everyone, my name is Moran Nechushtan. This is a joint work with Shiri Chechik, and today we are going to talk about the replacement path problem. So in the replacement path problem, we are given a graph G and the shortest path P from S to T. And our goal is to compute for every edge E in the path the distance from S to T in G minus E. In other words, we need to cope with a deletion of one edge. So in this lecture, we are going to talk about two variants. The first variant is called the M variant, where we are given a directed graph with integer edge weights between minus m to m, and we assume that the graph doesn't contain negative cycles. The second variant is the planar variant, where we are given a directed planar graph with non-negative edge weights. This table summarizes some of the prior work regarding the replacement path problem. In lines 5 to 7, we cover the M variant. In lines 8 to 11, we cover the planar variant. And we will get back to this table at the end of the lecture. Let's define the notion of a detour. Let D be a path connecting two nodes in the path P, in this case Vi and Vj. We say that D is a detour if its intersection with P is only the first node Vi and its last node Vj. And such a detour divides the path P to three parts: prefix D, SD, and suffix D. Let us prove simple lemma that is used by various algorithms. Let E be an edge in the path P, and suppose that T is reachable from S in G minus E. Then there exists a shortest path from S to T in G minus E of the form prefix D, D, suffix D, where by dot I mean a concatenation, where D is a detour skipping E. The proof is very simple. Let the yellow path be the shortest path from S to T in the graph G minus E. As you can see, the yellow path goes out and in from the path P a couple of times, and the idea is that it's enough to do so only once. So the path from S to Vi can be replaced by the shortest path of P from S to Vi, because P is the shortest path. And the same is true for the path from Vj to T. And now we got the desired form of the path, where is a concatenation of prefix D, D, and suffix D, where D is a detour skipping E. In the next slides, we are going to see how to reduce the replacement path problem to a new problem where we need to compute shortest cycles for all edges in a shortest path. And later on, we will see how to use this reduction to provide a very simple solution to the two variants, the M variant and the planar variant. Here is the first observation. Let D be a detour. If we flip the orientation of every edge in the path P, like so, then the concatenation of D with SD forms a directed cycle. The second observation is regarding to what we are actually looking for to minimize. So let E be an edge in the path P and let D be detour that is skipping E. So we are looking for to minimize the weight of the replacement path, which is the weight of the prefix plus the weight of the suffix plus the weight of the detour itself. Notice that the weight of the prefix plus the weight of the suffix is equal to the weight of the whole path minus the weight of S of D. Now, the weight of the path P is fixed because S and T are fixed in our problem, and the shortest path P is fixed in our problem. Therefore, the weight of P is constant. Hence, when we are looking for a detour that minimizes the weight of the replacement path, is equivalent to find a detour that minimizes the weight of D minus the weight of S of D. Let us combine the two observations together. So the first thing we do is to flip the orientation of every edge in the path P, like so. And now the weight of the cycle is equal to the weight of D plus the weight of S of D. if we also negate the weight of every edge in the path P, then the weight of the cycle becomes the weight of D minus the weight of S of D, which is what we are actually trying to minimize, as we have said in the second observation. Now, at this point, it is obvious that the weight of the minimal cycle containing E is no greater than the minimum of the weight of D minus the weight of S of D for all detours that are skipping E. That is because every detour that is skipping E defines such a cycle that contains E. As we will prove later, there is actually an equality in this equation. So let's define the transformation more precisely. So we take the path P, and we flip the orientation of every edge, and also negate the weight of every edge. And the resulting path is denoted by PR. Similarly, we define a new graph denoted by GR, which is identical to G, except that we replace the path P with PR. Now I'm going to state two lemmas regarding the graph GR. The first one is that the graph GR doesn't contain negative cycles, so the transformation of replacing the path P with PR hasn't created negative cycles. And the second lemma is that the path PR is the shortest path in the graph GR. So we assumed that the graph G doesn't contain negative cycles and that the path P is the shortest path in G. And now, in the new graph GR, we know that there is no negative cycles and also that the path PR is the shortest path in GR. So I'm not going to prove those two lemmas because we are short in time. So we will take them as they are. Yet we will prove the following lemma. Let E be an edge in the path P equals to UV. Suppose that V is reachable from U in GR. Then there exists a minimal cycle containing ER in GR of the form of concatenation with D and the path that is skipped by D, which is SRD, where D is the detour skipping E. So let's see why this is true. This is very similar to the detour lemma that we had before. So a general cycle that contains ER in the graph GR might look like this, like the yellow path. So because we know that the path PR is the shortest path, we can replace the part from U to VI with this subpath. And the same is true for the part from Vj to V. And that's it. So basically, because we know that PR is the shortest path in the graph GR, we use this to prove that the cycle that we are looking for is of that form. Okay, so this slide summarizes everything we did so far. We denote by CE the shortest cycle in GR containing ER. And the following theorem states that for every edge E in the path P, the distance from S to T in the graph G minus E is equal to the weight of the path P plus the weight of the cycle CE. And we denote it by WR because we are talking about the graph GR. So why this is true? The distance from S to T in the graph G minus E is equal to the weight of the minimal replacement path. And we can assume that the replacement path is of the form prefix D, D suffix D. As we've seen by the second observation, we can write it as follows, as the weight of the path P plus the minimum of the weight of D minus the weight of S of D for all detours that skips E. Now we can say, as we've seen 1 minute before, that the weight of the minimal cycle that contains E is of the form of D concatenated with the part that the detour skips, which is SRD. So therefore we have equality. So what can we say about the minimal cycle containing ER in the graph GR? Well, it's composed of the A GR with the shortest path from U to V, and therefore its weight is equal to the weight of ER, which is minus WE, minus the weight of E, plus the distance from U to V in the graph GR. So if we summarize everything together, we have this equation, this formula. So basically, if we want to compute the distance from S to T in the graph G minus C, we need to compute a distance from U to V in the graph GR. Okay, now we are going to see how we can solve the replacement path problem for the M variant very easily. So recall that in the M variant, we have directed graph with integer edge weights in the range minus M to M. And the following theorem states that if we have a distance oracle A for directed graphs with integer weights in the range minus M to M, then there is an algorithm for the replacement path problem that runs in one pre-process plus n query time in OM notation. So why this is true, we just need to summarize everything we've seen so far. So we compute GR in linear time, then we compute the distance oracle for the graph GR in pre-process time, and finally for every edge UV in the path P, we compute the distance from U to V in the graph GR in query time and store the value the weight of P minus the weight of E plus the distance from U to V in the graph GR. And as we've seen before, this value is equal to the distance from S to T in the graph G minus E. And that's it. So the amount of queries that we ask for is bounded by the number of edges, which is at most n. In particular, if we use the distance oracle of Houston and Zwick, that is process time is O tilde of m times n to the power of omega, where omega is the matrix multiplication exponent, and its query time is O of n, then we can solve the replacement path problem in total time of O tilde of m times n to the power of omega. So before getting into the second variant, the planar variant, let's compare our result to the state-of-the-art result in the M variant. So in the M variant, the state-of-the-art result is by Vasilevskaya-Williams, which has almost the same running time as our algorithm. If you do consider polylogarithmic factors, our algorithm improves a running time by at least a factor of log to the power of 6, and is much more simple. So now let's see how we can solve the planar variant as well. So recall that in the planar variant we are given a directed planar graph with non-negative edge weights. Okay, so in the M variant we add the distance oracle of Houston and Zwick that enable us to solve the problem efficiently. So in the planar variant we have something similar, which lead us to consider to define the following problem, the multiple source shortest path problem, MSSP for short. So it's very similar to distance oracle, just with one constraint. So in this problem we are given a directed planar graph G with arbitrary edge weights. So notice that the edge weights can be negative, and a list of distance queries, source target, where all sources share the same face in the planar graph. So we are restricted for distance queries such that all the sources share the same face. And I also assume that we are given a shortest path tree rooted at one of the sources. And our goal is to compute those distances. For all source target in the list, we want to compute the distance from the source to the target. So let's see an example for this problem. So assume we are given that graph G. So the input is this graph and a list of some distance queries. So let's assume that our face is the external face, which is composed of the blue nodes. So in the list of the distance queries, the source must be a blue node. And we also are given a shortest path tree rooted at one of the blue nodes. And our goal again is to compute the distances in the given list. Okay, so recall that for any edge E equals to UV, we can compute the distance from S to T in the graph G minus E with one computation of distance from U to V in the graph GR. So the idea is that we will compute the distance from U to V in the graph GR by invoking the MSSP algorithm. However, we have two slight obstacles because the MSSP algorithm requires all sources to share the same face and the computation of a shortest path tree. Now recall that the graph G, we assume that it doesn't contain negative weights, yet the graph GR does contain negative weights because we have created those negative weights in the path PR. So a naive computation of a shortest path tree in the graph GR with negative weights would be too time consuming, yet we will see how we can compute a shortest path tree in the graph GR in linear time for planar graphs. So let's define a new graph. Given the graph GR, we define a new graph H where we split every internal node in the path PR to two new nodes. So a node VI is replaced with two nodes, VIR and VIL, R for right and L for left. So basically H is identical to GR except of this replacement. And also notice that for a given node that is adjacent to VI, it has two options, whether it's to the right of PR or its orientation is to the left of PR. So if a node V is to the right of VI, we connect it in the new graph H to VIR. And otherwise we connect it to VIL. So notice that in the new graph, the nodes of PR share the same face. So this will enable us to use the MSSP algorithm to compute the desired distances. So one small notation, X and Y here play the role for left or right, and we denote the distance from VIX to VI plus 1 Y in the graph H by rho I XY for short. And the following theorem states that the distance from Vi to Vi plus 1 in the graph GR is equal to the minimum of all possible distances from Vi to Vi plus 1 for all the four possibilities: left left, left right, right left, and right right. So let's prove this theorem. The idea is that every path in H can be simulated in GR. What I mean by this is, consider the yellow path in the graph H. We can simulate it in the graph GR by replacing every node VJL and VJR with VJ. Like so. The converse is not true. For example, a path that crosses PR in GR, we cannot simulate it in the graph H. So this implies that the left-hand side is no greater than the right-hand side because every term in the right-hand side represents a path such that it can be simulated in the path GR from VI to VI plus 1. Therefore, the shortest path from VI to VI plus 1 is no greater than every term in the right-hand side, and we have this inequality. So as we have said before, a general pass in GR cannot be simulated in H because it might cross the pass PR, but this case doesn't bother us because the shortest path from VI to VI plus 1 doesn't cross the pass PR. So basically we have 4 possibilities. In this case, the pass PR exit from right and enter PR from right, and it can be simulated in H as in the image. Similarly, if we exit the pass PR from left and enter PR from left, then it can be simulated in the graph H as in the image. And similarly for the 2 other cases. So no matter what case we fall into, the shortest path from VI to VI plus 1 in GR can be simulated in the pass H by one of the terms in the right-hand side. So in total, we have this equation. Recall that the MSSP algorithm requires a computation of a shortest path tree. So in this slide, we will see how we can compute such a tree in linear time. So let T be a shortest path tree rooted at S in G, as presented by the green edges in the image. The lemma states that if we replace the path P with PR, then we get a new shortest path tree that is rooted at T in the graph GR, and we denote this tree by TR. So I'm not going to prove this lemma because we are short in time. It's not so hard to prove it once you know that the path PR is the shortest path in the graph GR. So what it tells us is that if we have a tree, shortest path tree in the graph G, we can convert it easily to a shortest path tree in the graph GR. So for planar graphs, we have a linear time algorithm to compute the shortest path tree for non-negative edge weights. So we can do so in the graph G to compute the shortest path tree rooted at S in the graph G, and then convert it to a shortest path tree rooted at T in the graph GR in linear time. And now our goal is to convert this tree to a new tree in the graph H. This is actually our goal because we are going to use the MSSP algorithm for the graph H. And we can do so as presented by the image. It's pretty straightforward. We just need to replace the path PR with the 2 new passes that going out from T, as in the image. So in this slide, we are going to summarize everything together. So let's state the theorem. Let A be an algorithm that solves the MSSP problem on a graph with n nodes. Then we can solve the replacement path problem in time that is proportional to 1 pre-process and 4 n queries. So let's summarize everything together. First, we create the graph H in linear time. Then we compute the shortest path tree rooted at T in the graph H in linear time. And finally, for every edge VI plus 1, we compute the right-hand side by 4 queries. So basically, we have 1 pre-process plus 4 n queries. And we store the value of the weight of P minus the weight of V plus the distance from U to V in the graph GR. And as we have seen before, this is equal to the distance from S to T in the graph G minus E. In particular, if we use the algorithm of Klein that solves the MSSP problem, which is running time, the pre-process time is n log n, and the query time is log n, then we can solve the replacement path problem in total time of n log n. So let's get back to the table. In this lecture, we have seen how to solve the replacement path problem in the M variant and in the planar variant, both of them in a state-of-the-art running time, as you can see in the table. As we've said before, in the M variant, we also improved slightly the running time if you do consider polylogarithmic factors. That's it. I hope you enjoyed the lecture. Thank you.